Welcome to our tutorial video for Computer Science 330, Physics 306. Today we're going to work with Wavedrom. This tutorial video is going to teach you how to utilize Wavedrom to create timing diagrams and gate level logic diagrams. And so we're going to use these tools to produce our solutions for the homework problems due this week. So the first thing to check is, do we have Wavedrom installed? So I've just opened Python environment, and I'm saying import Wavedrom, and yes, we do have it installed. So if you don't have it installed, I recommend just running pip install Wavedrom. And so it says I already have it installed. What if I uninstall it, just so you can see what happens when you uninstall using pip? Now, keep in mind, this is a Linux system, so I'm assuming that you have some way of running Python on your own systems, and that you can install packages. If you know how to do that, then hopefully this all looks familiar. But if you don't, there is a handy way of dealing with Wavedrom to start, which is that if you go to the Wavedrom website here in my left panel, there is actually an editor where you can write a little object, and it renders the logic diagram or the timing diagram, whichever it is. So once again, that's wavedrom.com, and then you'll be able to create using that as well. But if you're able to install packages, and hopefully you are on your own system, then you should be able to install Wavedrom using things like pip or conda. So let's try using pip. So apparently it didn't fully remove it, so it took it from wherever it was cached. So let's import Wavedrom. Okay, so that we can do that. Now what we're going to do is go to special folder where I've got two examples. I'm going to post these examples to Moodle. But let's open a code editor, and we'll just include these files as the files we're opening. So I'll get rid of some of this welcoming guide stuff. And let's look at a gate example 1. And you'll see that it has the basic structure that you might see if you opened wavedrom.com and went to the editor for a timing diagram. So we import, this is the Python version, so we'll have to import Wavedrom and then make an object called signals, which is nothing more than a multi-line string, and then we pass that big old string to a function called render. And render will create an image file, and it'll store that image file into this variable SVG. SVG, then we can use the save as method of SVG to create an actual file on our system. But what are we actually creating? Well, so look at this string here, signals, and then it's triple quotes, so you can have a multiple line string here. But it looks like a dictionary, right? There's a brace here and a brace there, and then we have some sort of key with a colon, and then the value that follows is going to be an array. But what goes in the array? Well, each element could be another array, but this is going to make a logic gate example. So, right. So let's just say that the output is going to be called X. What should the output X be? Well, whatever it is, let's make this, so this is going to be, a collection of objects. It's going to be all the data types are strings here. In fact, the entire thing is a string because it's all within triple quotes, but that's just for the benefit of the Wavedrom render function. So the output here is X, and a sign here just tells the render function that this is going to be a gate diagram and not a timing diagram. So the output's going to be x, and so a sign is equal to x, but then what are the inputs? What if we just said simply a and tried to run that and see what happens? So over in my command terminal, I'll just say Python 3, and I'm actually editing the file gate example. So that produces an error. So we have to have something more than just some input equals the output A. I think we have to have some sort of gate. So what if, as a string, we add the ampersand A comma B? What if we do that? Okay, so that apparently worked. And so there should be some file called gateexample1.svg, and there is. So if I type ls, that just lists the files that are in this current directory. So if I remove it, then now there's just the code only. So I'll run it one more time. There's just the code, and then I'll run my Python 3 example. Okay, so it did something. I hit ls again. So now there's the image file. EOG happens to be a program called Eye of Gnome. That's my image viewer on this system. So if I say gate example and we view the file here, there is no background, so it's just there's a default checker pattern back there. But you can see that X is the output. There's an AND gate, and A and B are inputs. So how do we turn this into a PDF? I happen to have installed a program called Inkscape. It's an image converter, and so there are many ways of converting SVG and PNGs and other file formats to PDF. So this is how I'm going to do it, but this is up to you. So if I say Inkscape gate example 1 SVG, I can say maybe export PDF and equals how about gate example 1.pdf. So it warned me that's an older operation, but still, let's take a look at the PDF version. And so now you see it has a white background, and this is a PDF file, so we can incorporate it into documents. So there's your AND gate, A and B are the inputs, and then X is the output. So what if, for example, we want to do something more complicated? Well, what's the next most complicated thing? What if we just add more inputs, so C, D, like that? Will it assume that I mean X is the output of and then for these inputs? And well, what kind of object am I creating here? There's a bracket and a bracket, and then within that there's brackets, and then within that thing there's more brackets. So this is a list of lists, basically, with all the data in those lists being the form of a string. So if we now run again the code, same procedure, just use Python to execute that code, and then we're going to convert the output to a PDF, and then we'll look at that PDF. Now the PDF shows that there's 4 inputs, A, B, C, D, and they're all being ANDed, and then the output is X. So that is one way to make a complicated, or the next most complicated gate level diagram. What if, for example, you took this whole thing, you can start to add complexity. So that maybe could be one idea. I'm going to copy it. And then what if instead we drop down a line, and I'll say X is the, let's say, OR of two things. Let's say this, and then that again. And then we'll close the OR, and then we'll close X, and then we'll close the assign. So what if we do something like that, just adding complexity? That there could be no, there's no error, so that's good. We'll convert and then view. And so now we have, you could see how we could quickly build up complexity. So now I have a 4 input AND gate, the same exact thing. I know that's redundant, but um, the wire heading out of the upper AND gate and the wire heading out of the lower AND gate are then being ORed, and X is the output. So you can imagine some really complex tree of gates to form a complex logic circuit. And so that's going to be useful in building up our solutions to these problems. So in the next video, we're going to cover a review of timing diagrams, which was also in a prior video for the course. And I'd like you to use these videos to produce your solutions for the homeworks this week. Welcome back to our tutorial video for COSC 330 and Physics 306. This next bit will be about timing diagrams, creating traces with Wavedrom and Python. So hopefully you now have the ability to make gate level logic, and using a prior tutorial video, hopefully this timing example will look familiar. And the goal is to render images of traces and logic gates to use those to produce the solutions for the homework. So let's have a look at timing example 1 on the right hand side in my code editor here. So we import Wavedrom as usual, and we create one long string. So we use the triple quotes function of feature of Python, call it signals, and then we're going to make a dictionary, and instead of assign, as in the gate level example, we use signal. So braces, quote, signal, and then colon, and then what follows is the data for the actual timing trace. Now, it's going to be a list of dictionaries. So with assign, it was just lists of lists. And then, you start with the output, and then what gate is it, and then a bunch of inputs, and then as long as you close your brackets correctly, you've got your gate level diagram. But here we have to have names for the the input lines, and then also we have to call it either a wave or some other form of data that's going to be displayed in the timing trace. So for now, let's just stick with wave as the type of data. And the name, you can put whatever you want. So it'll be string colon, and then your actual string for the name of that digital line, comma, and then the next element of the dictionary is the key value is the you just say wave and then colon, and then this string here is the special part which designates whether whether the lines are high or low, and what shape and form they take. There's all kinds of things that can go in this string, but this is the basic idea. So let's just make sure that's saved, and then we'll go over to the command terminal to run timing example 1. And it succeeds. As in the prior videos, we're going to use Inkscape to convert the SVG file to a PDF file. And so we do that, and then we look, now we have our gate example and timing example Python files. We also have the SVG files. The gate example is from the prior bit, and then now we have the timing example from this bit, and we've also got our PDF versions of those same diagrams. So let's look at the timing diagram version. Zooming in here, we have the clock signal, and then the data line, D0. And so the clock signal is at some frequency, and the data line starts at 0, and then looks like after 4 clock cycles, in the 5th clock cycle, it goes high, and then all the way back over here, it goes low again. And so you see that reflected here, which is the in this dictionary describing the data line, not the clock line, but the data line. You see it says low, and then repeat, 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 and then high, repeat, 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 and then low eventually, and then repeat, repeat. So the dot symbol represents continue what you were doing, and then P represents clock pulse, continue, continue. Low and high are represented by L and H, uh, respectively. So what if we wanted to add a data line? And why stop it? Why stop at 1 when we can have 4? So let's go 1, 2, 3. Let's have them be all identical for now. Let's remove that last comma since it's the final element in the list. Remember, these are lists of dictionaries. So we have 5 lines. We're going to have the clock and then 4 data lines, which are all identical. And we'll run our code again after saving it. So we'll have Python timing example and then use the Inkscape to convert to a PDF. And we'll look at that timing diagram. We're zoomed in, so let's see if we can go across. Yeah, so now we have 4 data bits. You can call that a bit stream or a parallel bit stream, and they all are identical in their timing diagram. Now we can start to play with them. So what if we said, low, high, that's a J, low, high, and then what if I put another little interesting thing here? One nice thing is that you can check to make sure that they're all the same length very easily. So looks like I forgot to delete one thing there and then one thing there. So they should all be the same length, so the same number of characters, and that way you won't get any errors when you're trying to print something and one signal lasts too long. So we can run that code once more and then convert and look at the actual output. Let's just zoom out. And so you can start to see little changes and the waveforms are now different. And so one thing to do, you could, like, let's say, make the output of a counter by just altering the positions of L's and H's. I want to show you one more trick before we just leave you to solve the homework problems. You can group signals. So what if I put a bracket around some of my dictionaries but not others? So I'll just give it, like, here's a bracket, not a brace, but a bracket. And so the first element of the list there will be the name of the group, followed by what is essentially the rest of the elements in this list are now dictionaries containing the data. And then we close with a bracket. What happens when we do that? Let's save that and then go back to the command terminal to run and then convert to a PDF, and we'll look at the PDF. So now the only difference is that you see, let's zoom in. So now you see this nice grouping symbol. So you can have different bit streams or different parallel or serial bit streams to signify different parts of the problem. So for example, what if there's a part A or B? You can put the solution to part A in one group, copy paste solution to part B in a second group. So what I expect you to do is create timing traces with this sort of code, and then gate logic with this sort of code for each homework problem, and show me both the input and output timing trace and the gate level logic for each of the 3 exercises assigned. So this has been COSC 330/Physics 306 tutorial video. Please email me at jhansen2.edu with any questions. Thank you.